Welcome to another unannounced, unscripted, unprepared episode of I Could Science That. Probably just me today. I'm going to go over this Wang paper. You know what? Let me throw a link up in a banner. I'll do that. Let's do that. Let's make a banner and throw that on the screen. So, okay, this will be available for unrecorded later, so you can watch this. So what's going on today? What's this about? Background. The last stream that I did, I had some guests on, and we talked about ether. We talked about special relativity, and they referenced this paper, and particularly the author of the paper, whose name is, I'm going to say Ruyong Wang. And the co-authors Yi Zheng and Aiping Yao. So those are three, Chinese names. They were evidently studying here in Minnesota. Actually, I'm in the USA. I'm not in Minnesota, but here in the USA at St. Cloud University in Minnesota. So my understanding is these are probably graduate students at the University of Minnesota, or maybe they were already PhDs or postgrads. Postdocs. I'm not really sure, but these are. This is a published paper. It's a legit paper done at a university here in the U.S. And my two guests, Alan and Tom, referenced this work, and particularly the lead author, as saying that this work refutes special relativity. So let's take a look at the paper and see what it says. Okay, I'll also throw a link here in the comments, easier to click on. And I'm going to start just sharing. Present, screen share. I'm going to share, just going to share the whole window. What could go wrong, am I right? What could possibly go wrong? Okay. So first off, if you do a search, you can find it here on the archive.org, however you pronounce that, Cornell's little archive. And then link to a downloadable paper, no paywall or anything. You can just come and look at it. So this is good. I like that. Paywalls in science, am I right? So here is the paper called Generalized Sagnac effect, or however you pronounce Sagnac. I say Sagnac, but that's not right, obviously. Okay, what is it about? Let's do just a little background, I guess. The Sagnac effect is something I think most of us here in these circles are semi-familiar with. The idea is that if you send a beam of light around opposite directions around a circle, that if that circle is rotating, that the path of those light is different from going with the rotation or going against the rotation, and that creates an interference effect when the beams meet back up in the middle. Hopefully everyone kind of gets the gist of what that is. It is the basis of these fiber optic gyros, and fiber optic gyros are a famous thing in these circles, certainly. Thanks, Bob, right? So yeah, fiber optic gyros, though, most of us don't have one. They are pretty expensive. Here's one on Alibaba that you can pick up for, evidently $5,000-$6,000. That's pretty pricey. Although I do like to point out, if you go shopping, you can find them a lot cheaper than that. So if somebody really wanted to do an experiment on this, and maybe do a little fundraiser, I would be surprised if you couldn't raise enough money to buy a used fiber optic gyro here off of eBay or something like that, if you really wanted to know. But getting back to it, the Sagnac effect, my guests, Alan and Tom, last time agreed absolutely that the Sagnac effect is measurable. This is not under contention. I mean, Bob showed it, right? We've seen it. We know that it's a real thing. And here's the Wikipedia page. Wikipedia is not the ultimate authority of all things. But if you're trying to learn a new topic, I recommend people start here. This is your starting point. Do your intro to a new topic. I wanted to highlight this piece of the Wikipedia page, which is that Sagnac himself thought that his experiment was inconsistent with special relativity. He believed that his results constituted proof of the existence of a stationary ether. That's what Sagnac thought. But read the next line. However, as explained, in the paragraph above, it had already been shown before Sagnac even did the experiment. It had already been shown that this is consistent with special relativity, and draw your own conclusions about that. It's pretty easy to show something that we typically do in the classroom, that a Sagnac interferometer will show the rotation under special relativity. It's completely consistent with relativity. Don't let anyone tell you that it isn't. Okay. If they say, no, it's not, the experts in the field, people who understand and teach special relativity, can take you through the equations and take you through all the math and show that it's completely consistent with special relativity. Great. So the fiber optic gyro, based on the Sagnac effect, it measures the rotation of the device. And we've typically said that's the absolute rotation. Okay, so let's look back at the paper again. What do Wang and Zheng and Yao have to say about this? They have a generalized Sagnac effect, which includes linear motion, not just rotation. And they start with some intro where they talk about what we understand of regular, like rotating, like beam going clockwise, beam going counterclockwise. So we're talking about rotation and how that works. They go on to talk about how people understand that this can measure rotational motion. Yes, and I think we all now, hopefully we understand that. But what are they going to do? They're going to do linearly moving glass fibers. And now we all go, wait, Sagnac is about rotation. It's not about linear motion. What's that about? That can't work. And I think that's most people's initial reaction. That was my initial reaction, was no, you can't measure linear motion with light. That's, special relativity says specifically we can't measure linear motion. That's one of the foundational principles of special relativity. So let's go on and on. The paper is short. It's only 3 pages. But it took me a little while to completely get my head around what it was they were building. And so let's cut to the chase, and I will not leave you in suspense anymore. Let me describe for you what it is that they built. Here we have the picture, their own diagram, and I'm like, what? Right? And you read the stuff, and it's a little hard to fathom exactly what this is. So let's go through the parts here. We have a fiber optic gyro. It is on a conveyor belt. It will be moving at a consistent speed. It will not be accelerating. It will be moving at a constant speed, v, linear velocity. So there's a fiber optic gyro moving at a linear velocity indicated here to the left. And then when they do the measurement, The phase difference in the light inside the fiber optic gyro has just a dead-on perfect linear relationship to the speed of the conveyor belt. And you're like, what? Doesn't that violate special relativity? A linearly moving fiber optic gyro measuring its linear speed. Now let me I'm just going to pop back here. Middlewell says hi. Sean says hi. Or well, hello. Hello, folks. And so like I've got the screen, I've got the screen right now. You're like, that's not right. That would completely violate special relativity. That would completely invalidate the use of fiber optic gyros in aircraft, right? That wouldn't work, right? Like this cannot be right. What have we missed, right? And there's a lesson there, right? There's a lesson right there, which is when you see something that appears to violate the laws of physics as you understand them, I mean, it could be that you've misunderstood what's going on here, right? Or it could be you've discovered a whole new branch of science. Think about your own experiences in the past. How often have you made a mistake? And how often have you discovered brand new branches of science? Right, exactly. Me too. I must have made a mistake. What was the mistake? Let's look closer at this device and try to understand what's going on. Here it is. We have a fiber optic gyro. The light from the fiber optic gyro, the laser light going through the fiber, comes out of the gyro into a fiber optic cable. And the fiber optic cable goes around this wheel and around back here, and then around this other wheel, wrapping it back around, wraps around a few times, around like in a racetrack pattern. And then it comes back out and goes back down into the fiber optic gyro. So the light that the fiber optic gyro is measuring isn't just going through the fiber optic gyro. It's also going through what I call the racetrack. It's going through this oval, like racetrack pattern back and forth across these two freely spinning wheels. And what's this red thing? What's the red thing? The red thing has attached the wheel to the motion of the conveyor belt. It's coupled, meaning that these straight sections of the racetrack are moving at the exact same linear speed as the fiber optic gyro on the conveyor belt, right? And this is the key. The key here is that the light is going around this racetrack, and the racetrack is, say it with me now, spinning. It's rotating, right? The racetrack is rotating. What are we measuring? We're measuring a rotation, right? This is not measuring absolute linear motion. What it's really measuring is the difference in linear velocity from velocity going to the left here and velocity going to the right here. The difference there is what is causing the phase shift. And that is something that, yeah, of course we can measure, right? We can totally measure that. That's cool. Let me pop back and see if there's any comments to read. We got a hi. Yeah, 11th Chimp said, that thing is completely unremarkable. It measured relative velocity. And yeah, you're right, 11th Chimp. That is exactly right. Yeah, they could have done maybe a simpler thing. I give them some credit. This is a fairly novel invention, this setup. I don't know what application it would have, but maybe we could come up with some applications for it. I don't know. Presumably it's more sensitive than a simple Doppler shift measurement that they could have done. Right? You could use Doppler shift to measure the differential velocity. We know this. but they're doing interferometry to measure the differential velocity. That's what's going on. So what else do I want to show about this paper? I mean, that's really the long and the short of it. There's nothing in this paper that violates special relativity at all. The only thing novel to it is they have sort of taken the idea of what the Sagnac device, the Sagnac experiment was measuring, and they've sort of extended it. Much like I was showing in that previous stream, I was showing this, and I was trying to explain that that if you have different flow speeds side by side, like this arrow and this arrow are pointing parallel, but they are different lengths, and that creates a rotation. In engineering, that's a rotation. In physics, that's a rotation, even though it's not turning in a circle, because the speeds are different. That's the equivalent of a forward speed plus a rotation speed. And they have done the exact same thing here. They've done the exact same thing with their fiber optic cable. Instead of just going around in a circle, as the classic Sagnac does, they have it doing this, going like this. Two beams going like that. And that's a rotation also. But the math is different for this configuration than the old Sagnac. So we don't see the area enclosed by the fiber optic cable as part of the equation. Instead, we see the length of the fiber optic cable in the equations. And they take us through the equations. And yeah, I mean, if you read this paper, they do the math as well as the experiment. It's not just an experiment. They do the math as well. And this math is all based on special relativity. This is a paper about special relativity. It's a novel approach to look at special relativity, but there is nothing, I find nothing in here where the authors make any claims to be violating special relativity or overturning it or anything. Merely that they have a fairly novel look at a particular type of device that leverages special relativity in a different way. And that's really it. That's the whole paper right there. I will also point you to this little diagram. I found this diagram very helpful for understanding the other one. This one, I was a little confused about, like what is going on? Is this turning? It wasn't clear to me that this whole apparatus is spinning around in a racetrack. That is what's happening. That's what they're showing with the V's. Now that I understand, it seems very simple, but I was confused for a long time about what are they showing here? Is this like the direct path of light, or what is that? No, that is the cable going around like that. And that's clear right here in this diagram, where they do a simpler example of, they have a fixed piece of fiber optic cable, and then they have another piece of the fiber optic cable that they're just shoving to the left. They're just moving it to the left, and they have slack connecting the two sides so that they can just shove part of the cable to the left. And that's what they're measuring. Okay, so that's it. I'll turn off this share, see if anybody has anything to add. Okay. Yeah, I've seen the bottom. Okay. What is Alan's thoughts on your take? I'll put that up there. I talked to Alan about this last night. We discussed it, and just like I was completely confused at first about what this setup was doing. He was as well. He definitely started with the thought that this was a fiber optic gyro on a conveyor belt, and that Wang et al. Had measured the motion of the conveyor belt using a fiber optic gyro. It wasn't clear to him that what Wang had measured was the speed the counter rotation or the counter motion of two opposite arms of a racetrack. And when I explained that to him, he totally understood it and agreed with that. And then he is taking some time now, I think, to evaluate exactly what that means, and so forth. Okay, what else? Did you also do an evaluation of some papers that use GPS to show the variance of C? Yeah, we'll get to those. We'll get to those, I think. Short version is no, they don't, but that's okay. Okay. Yeah, 11th chimp. You have seen this. You have seen this paper before. It's new to me, and so I thought it was really interesting. I still think it's fairly interesting. And some of the stuff I've read from Wang following up on this, he does go into some stuff where he no longer supports special relativity. But in 2004, with that experiment, he absolutely supports special relativity, and this paper completely supports special relativity. Cool. Anything else to add? Any questions? All right. I guess we can wrap it up there, call it a nice short little one. In summary, I don't know if the term generalized Sagnac effect has ever taken root. I haven't heard that anywhere else. Maybe that's a term that has or will take off. It is a consistent part of special relativity if you have counter moving velocities, a cable going this way and a cable going that way, and you shoot light in opposite directions through them. The one going with the cable has a longer path to travel than the one going against the flow of the cable. This is the standard explanation of the Sagnac effect. And so you can do that by rotating the cable, or you can do it by moving the cable on a path. Either one works. And so there you go. Special relativity confirmed. Thank you, Wang et al., for an interesting invention. Okay, I guess that's it for today. Thanks for showing up, you guys, and keeping me company. Good to see you all, as always. See you in the next one.